My name is Hui Guo. I'm a PhD candidate at UC Davis. Today, I will present a joint work with Professor Cindy Rubio on error-inducing floating point input generation. We know that floating point arithmetic generates and propagates rounding errors. These rounding errors will be accumulated into the program results. That is to say, each output of a floating point program is associated with an error. In most cases, the error is small, but the error can be very large. Knowing what inputs will trigger a high error in your program is important. This leads to the problem we try to solve in this way, to generate floating point inputs to trigger large numerical error. The state-of-the-art error-inducing input generators falls into two categories. In the first category, the techniques are randomness based. They treat the program as a black box, and they use a set of heuristics to search through the entire input domain to identify error-inducing inputs. This set of techniques are inefficient, especially when the input space is very large. In the second category, the input generators are conditional number based. They treat the program as a function on an input variable x, and they compute the condition number of the function with regard to x to identify error-inducing inputs. However, this set of techniques, they can only handle programs with one input variable. The task in this work is to generate error-inducing inputs for programs with multi-dimensional inputs, which indicates very large input space. First, we observe how an error-inducing input triggers a high error. We use a program that implements recursive summation. As an example, this program takes an array as input, and it computes the sum of the array elements. We manually crafted an input array that can trigger a high error in this program. For this input array, there's 3 additions. In the first addition, it adds A3 to A2. The result is -98. E here represents the error in the result. As we can see, the value in A2 is rounded off in this operation. This is a case of precision loss. In the second addition, it adds -98 to A1. The result is 0. This is a cancellation. After the third addition, it computes the sum of the 4 elements as 1.1 times 10 to -15, and the error is -1.2 times 10 to -15. This is a very high relative error. Our insight about generating error-inducing inputs is that we should explore the operations where precision loss and cancellation occur. We designed and implemented the tool FPGen. It's an error-inducing input generator that uses symbolic execution. There's 3 main modules in FPGen. Each module is represented by a color. The first module is accuracy check injector. It injects inaccuracy checks into the program P to detect precision loss and cancellations. The second module, concretization and symbolic execution, they iteratively partition the input variables into 2 groups. Variables in one group are concretized with random values, and variables in the other group are symbolized for symbolic execution. We then monitor the status of the symbolic execution engine. If it times out, we will reduce the number of symbolic variables by a half. If otherwise, we will redistribute, concretize, and symbolic variables in the input variables and redo concretization and symbolic execution. This process can be repeated as many times until time is out. The third module, error measurement, takes a set of inputs generated by symbolic execution. It measures the error triggered by each input to identify error-inducing inputs. In our evaluation, we collect 21 programs that take multidimensional input. Specifically, we include 3 summation programs that take arrays as input, and 9 matrix computation programs from the Mosaic library that take vectors and matrices as input, and 9 statistic programs from the JSL library that take arrays as input. We compare FPGA to 3 baselines. First, the random generator. Second, the state-of-the-art error-inducing input generator S3FP. S3FP is randomness based. Third, the symbolic execution baseline ClearFloat. ClearFloat is a symbolic execution engine for floating point programs. We also used ClearFloat as the symbolic execution engine in FPGA. We show the results of our experiments in a figure. X-axis indicates the benchmarks. The Y-axis indicates the maximum error each tool triggered in the benchmark. The Y-axis is in log scale. Each input generator is represented by a color. As we can see in most programs, FPGA triggers the highest error across the 4 input generators. And there's 4 programs, none of the input generators can trigger a large error. And there's 3 other programs, S3FP triggered the highest error. Our guess is that in these programs, FPGA failed to trigger a cancellation. A summary of the results: first, out of 21 programs, random generator and S3FP can trigger an error in 13 programs, and ClearFloat failed to trigger an error in any of the programs. And FPGA triggers an error in 20 programs. Regarding to the magnitude of the error, FPGA triggers an error that is around 10 to negative 6. It is more than 2 orders of magnitude larger than the error triggered by S3FP. To conclude, we designed and implemented FPGA, an error-inducing input generator that uses symbolic execution. Thank you.